All right, let's jump right into this structural engineering masterclass. Today, we're going to bridge that massive gap between pristine, perfect textbook calculations and the downright chaotic reality of a construction site. We're going to take the mathematical perfection of engineering theory, and we're basically going to smash it against what actually happens when boots hit the mud and the concrete gets poured.
Here's the roadmap for today's explainer. We'll start by tracing structural load paths, then move into bending, shear, and moment. After that, we'll tackle controlling flexural concrete cracking, weigh ultimate versus serviceability limits, and wrap up with the ultimate site reality check, placement errors.
Section 1. Tracing structural load paths.
Okay, picture animated force arrows flowing from a concrete slab, down through a beam, into a column, and finally resting at the footing. We can actually map that exact physical journey. The U-star index mathematically tracks this by determining the internal stiffness of every single point inside the structure. It basically maps the ridge line of load transfer. Meanwhile, the strut and tie model visualizes this as an internal truss system. When you push it to the limit, after significant cracking happens, those complex compressive stresses literally straighten out into direct struts, while our steel reinforcement acts as the tension ties. But keep in mind our first big site note. Textbooks assume perfect geometry, but out in the field, you're constantly dealing with unexpected structural voids or spontaneous field alterations.
Now here's where it gets a bit tricky. Don't be fooled by stress concentrations. When you analyze a member with a central hole, you're going to see astronomically high von Mises stress right at the edge of that hole. But you absolutely cannot conclude that the main load is passing through that highly stressed area. Why? Well, because the hole has no material. It literally cannot carry the load. The U-star load path index cuts right through this noise to show us the true path of the force. So keep this fundamental rule of thumb locked in your brain. Loads are lazy. They will absolutely always hunt for the stiffest, most direct route to the ground. If you understand exactly where your structure is stiffest, you know exactly where the force is traveling.
Moving on to Section 2. Bending, shear, and moment.
Whenever a load hits a beam horizontally, it creates bending stresses. The crucial concept here is that a beam's neutral axis dictates exactly where the material starts behaving differently. Above that neutral axis, we're relying on concrete to crush together in the compression zone. But below it, the beam desperately wants to pull apart. Because concrete is notoriously weak under pulling forces, this is the tension zone where we rely entirely on steel rebar to hold the whole shebang together. And a quick reality check for you, while textbooks love to assume perfectly pinned supports, most real-world connections have some degree of fixity. You always have to watch out for unintended moment transfers.
And that brings us to why we use standard drawing conventions for moment diagrams. To really visualize deflection, just imagine an exaggerated, deformed beam literally smiling at you under a positive bending moment. That smile warps the element into a U shape. In structural concrete design, we often draw the positive moment right on the tension side, the bottom of the smile. That simple visual cue tells you exactly where you need to place your tension reinforcement.
Now, this mathematical principle is an absolute lifesaver for quickly verifying your design models on site. Schwedler's theorem proves that a constant distributed load will inevitably yield a linearly varying shear diagram. And here's another classic rule of thumb when you're out in the dirt. To quickly gauge if a beam is appropriately sized before you even run the diagrams, just check if its depth-to-span ratio is hovering around L/20. If it's wildly off from that, your moment and shear diagrams are definitely going to spell trouble.
Section 3. Controlling flexural concrete cracking.
The Transportation Research Board data maps out this dynamic cracking process beautifully. We can see how crack growth aggressively accelerates from tiny microcracks to rapid macrocracking under stress. The brilliant solution for two-way slabs relies on understanding that stress concentrations develop right at the grid nodal points, basically where the rebars intersect. That orthogonal reinforcement grid actually controls the specific fracture energy. By spacing the grid perfectly, you force the concrete to form preferred, narrow, orthogonal cracks instead of massive destructive fissures. But remember our site reality? Textbooks calculate exact theoretical crack widths based on assumed steel strain. But out during a real pour, concrete cover thickness varies wildly, which drastically alters how those cracks actually propagate.
See that tiny number? 0.004 inches. That is the absolute maximum permissible flexural crack width for water-retaining structures, according to environmental exposure codes. To put that into perspective, it's practically microscopic. It really proves just how incredibly tight our tolerances are when we're battling long-term corrosion and deterioration.
So, here is your crucial rule of thumb for crack control. It is not just about how much total steel area you jam into the concrete. It's all about the geometric grid spacing. A tighter spacing of smaller diameter transverse bars absorbs that fracture energy way more effectively than using massive longitudinal bars that are spaced far apart.
Section 4. Ultimate versus serviceability limits.
Geotechnical codes essentially force us to juggle two totally distinct realities. First, we have ultimate limit states, or ULS, which ensures the building simply won't collapse. It's strictly about life and death, targeting a highly rigorous reliability index. Then we have serviceability limit states, or SLS. This ensures the building is actually usable, guaranteeing the floors won't sag so badly that doors jam up or that people feel seasick from the deflection. And for our side note here, while textbooks love to assume uniform soil bearing capacity, actual natural soil is incredibly variable. That's exactly why engineers have to use a 0.05 probability of failure along with highly conservative stiffness parameters.
When we map bearing pressure against the foundation width for a pad resting on sand, we get some fascinating data from the International Society for Soil Mechanics and Geotechnical Engineering. When you compare the ULS and SLS curves, there is a literal magic crossover point right at 1.5 meters, where our entire set of design constraints just completely shifts. Which brings us to a massive, time-saving geotechnical rule of thumb. If you know the size of your pad foundation is under 1.5 meters, ULS is absolutely going to govern your math. But the moment that foundation grows larger and the loads get heavier, SLS takes the wheel, because controlling that massive settlement and deflection becomes your most critical hurdle.
Finally, Section 5, Site Reality, Placement Errors.
Okay, this is the ultimate reality check. You can sit in an office and spend weeks calculating the exact neutral axis and the absolute perfect U-star load path. But all that pristine math goes right out the window if a worker out in the field flattens a complex hook just to make it fit inside the formwork. Altering that bend drastically reduces its anchorage capacity, which means the steel physically cannot fully transfer its stress into the concrete.
It's really a domino effect. When reinforcement placement strays from those strict neutral axis zones we established earlier, the structure's behavior fundamentally changes. If workers stagger laps incorrectly, say placing way too many splices in the exact same location, it creates intense bar congestion. This acts like a concrete dam, totally obstructing the mix from flowing and compacting properly, which leaves dangerous, hidden voids. Unintended stress concentrations build up rapidly, inviting premature cracking, deflection, and hidden shear dangers deep inside the element.
Go ahead and grab a screenshot of this. This is your ultimate explainer cheat sheet. It pulls together the most critical equations, concepts, and field guidelines from our entire breakdown today. It directly connects that pristine textbook theory right to the messy variables you actually need to watch out for on site.
And that wraps up our journey from theoretical load paths all the way to concrete site failures. But now I want to turn it over to you. If you could dictate the curriculum for our next explainer, whether that's seismic design, foundation settlement, or plastic analysis, what would it be? Let's build the curriculum for the next one together. Drop your answer in the pinned comment below, and I will see you in the next explainer.